Okay. Well, I'll close and we'll make a start. Okay. Thanks, Chris, for that introduction. Yeah. So I'm Liam Grimmett, and I'm a PhD student, as was said, at the University of Sheffield. I'm in my final 3 months now, so it's really is deadline day. But it's a pleasure to be here on Cyber Cafe Scientific and to talk to people about some of the work that I do. If I can say one thing about the introduction, maybe the title is a little bit oversold, Chris. You were right. Everything, galaxies is everything. So the statistics of everything is an interesting way to put it. But you'll be pleased to hear I'm not going to talk about everything tonight. In fact, I'm going to focus on a very small area of my research, just to kind of really whet the appetite for a Q&A or a discussion session afterwards. So as I said, usually people, when I tell people ask me what I do for a living, I give them one of two answers. I either tell them I'm a statistician, in which case I don't get many follow-up questions because statisticians are boring, right? Or I tell them an astronomer, which is far more interesting. So I have written this talk kind of leaning more towards the galaxy side of things, but I'm absolutely happy in the Q&A to discuss anything statistics or galaxies related, and I'll try, being the operative word, to answer questions as and when I can. Okay, so let's make a start, and we'll start at home. So this is the Milky Way galaxy. Okay, so this is the galaxy we all live in, right? And the first thing you'll notice about the Milky Way is that it's what we call a spiral galaxy because it has this spiral structure. Okay, now in terms of size, the diameter of the Milky Way is about 100,000 light years, and that means it's the distance that it takes light to travel. The distance light can travel in 100,000 years, and light travels at 300,000 kilometers per second. So that's incredibly massive, an incredibly huge distance compared to human distances. What does that mean? That means that the sun and the asteroids and planets and comets that are in our solar system actually fall into one of these spiral arms in a fraction of a pixel. Okay, but all the light you see in the Milky Way is generated within stars. Okay, and in fact, there are 100 billion other stars in the Milky Way, just like the sun. So most of them are a little bit smaller than the sun, but some of them are a little bit bigger. And I want to point out just a couple of other interesting things about this image. If you look very closely in the spiral arms, you'll see tiny red dots. Okay, and these red dots are where the Milky Way is producing new stars. So that's how the galaxy grows. Okay, now the Milky Way builds new stars by converting gas, okay, into stars, and that's how the galaxy grows. On average, the Milky Way only produces like one star the mass of the sun every year, so it's not a great deal. Okay, but it's not a lot of stars compared to the 100 billion it has. But yeah, this is our galactic home. Okay, now the keen-eyed of you will notice that down here it says artist concept. Okay, now the reason it's an artist concept is because we cannot take an image of the Milky Way. We can't take a picture of it because we're in it. So to take this picture, we'd have to leave the Milky Way, turn around and look back on ourselves. And given that we can't get out the solar system, we've just about got out the solar system, should I say, then there's no means by which we can take an image of the Milky Way. Okay, but that's not to stop you looking at it. Every star you see in the night sky probably resides in the Milky Way. And in particular, if you head out to a dark place on a dark night, out of the city, and you spend about half an hour looking up, you'll begin to see this pattern of stars that appears in the sky. It's a bright stream of stars. There's some dark patches that's used to galactic dust, what we call just plain old dust, really. Okay, and this is one of the most fascinating things I think you can see in the sky. It's truly remarkable to be able to look directly towards the center of the Milky Way in this spiral arm. Now, I didn't just start with the Milky Way because it's our galaxy and it's where we live. In fact, only 100 years ago, so that's merely just over the average lifetime of a human, this was all we knew. The galaxy itself comprised the vast majority of the universe. We didn't think that there was anything beyond the Milky Way, and we thought that, and you know, some things I've seen that estimates of the universe at that size were about 300,000 light years. So The Milky Way was the universe 100 years ago. Now, that means if I were giving this talk 100 years ago, everything I'm going to say from here on in couldn't possibly have been said, because there was only one galaxy. This changed just under 100 years ago. An astronomer named Edwin Hubble used a very simple trick. Okay, that trick is, the more distant an object away is from you, the fainter it appears. Now, I want you to think about when somebody turns on car headlights right in front of you, then you'll see that it's very, very bright and you can shirk your eyes and such, but you don't see that when cars are driving on the other side of the motorway. And the reason is because those two light sources are the same brightness, but one is further away. And Edwin Hubble used that to calculate the distance to this blue star cluster you see here. Okay, and it was called a nebulae at the time. But this blue cluster of stars you see here, so everything in this image is a star, but by some regions of gas, this blue star cluster was called NGC 6822. Okay, it was also called Barnard's Galaxy, but I shouldn't make jokes about eye tests. But Edwin Hubble used the fact of what I've just told you about light being fainter the further away is to calculate the distance to the star cluster, right? Because he said, if I could work out how bright some of these stars really are, I could use how bright they appear to calculate a distance. And the distance to NGC 6822, according to Edwin Hubble, was 700,000 light years away. And this is one of the earliest known records of when we managed to place an object comfortably outside the realms of the Milky Way. So just under 100 years ago was when we first started to discover that there were objects beyond our galaxy. So that's the history of extragalactic. That's the start of extragalactic studies. This is where it all started. But what's the image now? Now, the next image I'm going to show you, I think, is one of the most fascinating images, if not in science, certainly in astronomy. And this is the Hubble Ultra Deep Field. Okay. Now, this image is slightly different to the previous image.
And Liam,
well,
we have a question, which I think is a simple question. Is Hubble the same Hubble of the Hubble telescope?
Absolutely. So the Hubble Space Telescope is named after Edwin Hubble. I also have another question I've just seen here in the group chat. It said that, was Hubble expecting the cluster to be in our galaxy? I assume so. You know, there was no reason for us to believe that at the time that there were things beyond the realm of the Milky Way, as far as I'm aware. So I can only imagine he was incredibly surprised when he found the distance to this galaxy. Okay, so just to the Hubble.
One follow up from Twitter on that. How far was he expecting it to be when he found it was 700,000 light years?
Oh, I don't know. I imagine within 100,000. Just because, like I say, at the time it wasn't, there wasn't really much. I don't know. I don't know too much about what he was thinking, but I imagine he was pretty surprised. He probably checked his calculations a lot when he got to a figure of 700,000. That's for sure. But yeah, it certainly was the first. It's the first. Well, what we got is the first recorded instance of us detecting things that lay beyond the realms of the Milky Way. Okay. So as I say, that was the picture then. The picture now is this. So this is an image taken with the Hubble Space Telescope, which is, as was asked, is named after Edwin Hubble, the guy who calculated the distance to Barnard's Galaxy. And this image is slightly, and I said it's one of the most fascinating images in astronomy. I should probably explain myself. Every point of light in this image is not a single star. Every point in this image is an entire galaxy, which is probably got its own 100 billion stars, just like the Milky Way had. This is just unbelievable to picture, right? 10,000 points of light in this image, each with their own 100 billion stars. And remember, 100 years ago, there was only one galaxy. Well, we thought there was only one. Okay. But the picture doesn't stop here. I need to really explain why I think this is a phenomenal image. And this image is taken in a very, very small patch of sky. Okay, So if we were going to estimate the total number of galaxies in the universe, we can't just use the 10,000 that are in this image. And in fact, this image, the area of this image, is about an 80th of the moon in terms of area of the whole sky. An 80th of the moon. So it's incredibly small. And there's 10,000 galaxies in it. So if you correct for the fact that we see 10,000 galaxies in this direction, and we look at galaxies and we multiply it out to see how many galaxies are in every direction, we get that there are now 250 billion galaxies. Again, each with their own, probably about 100 billion stars. But it doesn't stop there, because there are images, there are pictures in this, there are galaxies in this image that are too faint for even Hubble to detect, which means there are galaxies we don't see in this image. Okay, which means if we correct for those galaxies that we can't detect with this Hubble Space Telescope, we estimate that there are now 2 trillion, so that's 2 followed by 12 zeros, 2 million galaxies, and a million being the American version of a trillion, 2 trillion galaxies in the universe. And 100 years ago, there was 1. Okay. I've just had, I've got a couple of questions here I can see on the question and answer, so I'll answer the first one from George and Barbara. How was he able to measure the brightness of the stars in that galaxy? Well, that's a really good question, actually. So the stars have intrinsically very different brightnesses, and it depends upon their mass, it depends upon things like their age, and it depends upon things like their metallicity. But there's a very subtle class of stars in which the luminosity, the true brightness of the star is related to the way it pulses. So stars can sometimes pulse. And what Hubble worked out was that some stars, they're called Cepheid variables, I think, pulse. And the frequency at which they pulse is proportional to their brightness. So he could calculate their estimated brightness by how often they pulsed, which means he could guess their intrinsic luminosity from that period luminosity relationship. And the other one, Sarah Voss, is how do you know if they're galaxies if you can't see them? Well, it's because they're not stars. So this image is taken for a very long time. And if there was a star in this image, it would completely saturate the image. So if you look at this, this is probably the nearest thing to a star, this object here, where you see this cross line. That's because at that point in the telescope, the CCD was called saturated, which means there's just too much light. So if there was an image, if there was a star in this image, it'd saturate the entire image basically. So we just know that the galaxies, and a lot of work has been done on some of these galaxies. There was actually a paper today looking at 4 of the galaxies that are in this Hubble Ultra Deep Field. So all these galaxies were have been studied in their own way. Okay, cool. Another follow-up question from Sarah. But you said that there were galaxies there, but you couldn't see them. How do you know that? That's a really good question. And the paper that actually used the conversion from 250 billion to 2 trillion was a bit debated, but I thought it was kind of a reasonable study. So one property of galaxies is that they're all different mass. They're usually different masses. So the mass of a galaxy is equal to the mass of all the stars of the galaxy. Now, if we look around the Milky Way, we see that we've got a series of very, very small companion galaxies. For example, NGC 6822 is very, very close to us, but it's very, very small. Now, what that means is we can look at how many small galaxies are in our local group, and we can assume that that is a representative sample. So the chances are that some of the bigger galaxies in the Hubble Ultra Deep Field you see here have smaller dwarf galaxies close to them that we just can't see. So what the paper did was that what it did was it assumed that there were more dwarf galaxies, we call them smaller galaxies, than had been recently predicted. How much of the sky has been imaged at this level of detail so far? So there are a few deep fields from Hubble. Now, I assume, George and Barbara, you're discussing the idea that the assumption that I've made that the universe looks like this in all directions. Again, these questions are brilliant. This is a tricky question, but because on small scales, the universe is not the same everywhere. Okay, there are usually clusters of galaxies usually forming clusters. They're not all spread out equally. But if you take the universe on very large scales, if you took a very large cube of the universe, in general, two cubes look roughly the same. So what we say is that what we say in terms of the universe is that it's homogeneous on large scales, but it's pretty inhomogeneous on small scales. It's a really good question as well, by the way. Okay, so Sarah Bohr asks, if a galaxy's mass is equal to the mass of the stars in it, then does the mass increase as new stars are formed? And if so, where does that extra mass come from? So the mass, so when we talk about the mass of a galaxy, I was a bit vague. I was referring to what's called the stellar mass, which is the stellar mass of a galaxy, which is the mass of all the stars that are in the galaxy. And it's also the mass of the galaxy, stars that have ever been in the galaxy. So sometimes stars die. So actually the stellar mass is equal to the sum of all periods of star formation in the galaxy. The extra mass comes from gas, sorry. So galaxies do have a gas mass as well, which forms the secondary component. So as galaxies convert gas into stars, the gas mass will obviously decrease, and then the stellar mass increases, which actually leads me very nicely onto talking about these galaxies in more detail. So as I said, using a couple of assumptions, we get to 2 trillion galaxies in the universe. And if you look at all the galaxies in this image, none of them are the same. Some of them are similar, but they have different colors. And just to talk about extending that question I've just answered, the very red galaxy you see up here is likely because that galaxy hasn't formed many new stars recently, which may mean that it's run out of gas. Okay, because naturally galaxies want to convert gas to stars. So if you see a red galaxy, okay, then older stars are usually redder, which means that there's not been any formation of new stars recently. Okay, and the red galaxy here is because the star population is old. Okay, and other galaxies you see here, blue galaxies, they're the opposite. Galaxies that are blue have hot new stars are blue. So galaxies that are blue tend to have had lots of star formation in recent times. I say recent times, astronomically recent times, not human recent times. Another good question. Carol Lynch asks another mass question. When considering the mass of the galaxy, are you only considering the mass of the baryonic matter? Okay, so for anyone who's unsure, baryonic matter is protons, neutrons, electrons, and anything built of them particles. I think I'm not a cosmologist. I think that's what baryonic matter is. I'm in error. So you're basically asking, am I talking about dark matter? No. There's another third. So I said gas mass and stellar mass. They're 2 ways to measure the gas of components of a galaxy. There's also something called the halo mass, which is kind of if you drew a big sphere around that galaxy, what is the mass of everything, including the dark matter, everything inside the galaxy? So no, I'm not talking about the dark matter content of galaxies either. Okay, so these are questions. I didn't expect such good questions. These are really good questions. So please keep the questions coming, and I'll do my best to answer them as and when I can. So as I said, the galaxies you see in this image are all different colors. Okay, so you've got red ones, green ones, blue ones, yellow ones, and that's just all because of different properties of the stars in the galaxy. Okay, there is a caveat that sometimes red galaxies are because of dust, but in general, the color of a galaxy highly represents the star population within it. Now, as you can see down here, there's some spiral galaxies. These are similar to the Milky Way. There are some galaxies like this yellow one here, which is just like a big football of stars. There's no real spiral structure to them. So galaxies come in all shapes and sizes and masses and colors and everything. But they do all have, oh, I've missed a slide. There's another interesting thing about this image that makes me think it's the most interesting image in astronomy. And that's because it's a 3-dimensional image. Okay, now you think, Liam, shut up, it's 2-dimensional, right? But what happens here is because we're talking about galaxies that are so far away, it means that the light has had to spend a lot of time traveling towards us. So the yellow galaxy you see in the bottom right-hand corner here is probably a few 100 million light years away. But what does that mean for us observing it? That means we observe that galaxy how it looked 100 million, hundreds of millions of years ago. Because light, when that light left that galaxy, it's a true reflection of what it looked like then. But by the time it reached us is 100 million, hundreds of millions of years later. So when you're looking at this image, you're not only looking at a small patch of ordinary sky that contains up to over 10,000 galaxies, you are looking back in time. This is as close as you can get to time travel. You are looking back in time. And just to help you visualize that, here's a picture of what, a model of the Big Bang, as it's called. If we imagine we're at this red dot right at present day, the Hubble Space Telescope has managed to look back and trace the faint, distant objects right back towards the beginning of the universe. Okay, which means that the image I just showed you is looking back in time, because some of the fainter galaxies in the background are further away. Therefore, you're looking at them how they looked longer in time ago, and therefore the third dimension of this image is time. And it really is truly one of the most fascinating images in astronomy. Okay, I'm just going to tick off the questions I've hopefully answered. If I haven't answered them, then maybe ask them again, and I'll try and give a better answer. Okay, so now we'll go back to what I skipped ahead. But despite all the differences in these galaxies, okay, so some of them are red, some of them are green, some of them are blue, some of them are massive, some of them less massive, and we know about this. They all have something in common. We're going to zoom in now on a simulation of the Milky Way. So here's a simulation of the Milky Way. We're going in, so it's what we call a disk galaxy. Kind of think of it like a CD. Okay, so we've had a look at the CD from face on. Now we're going in from the side. The dark patches are dust. You can see the bright objects that are stars. We'll probably zoom in roundabout past the sun now. But what I want to talk about for the rest of this talk is something right in the heart of the galaxy. Okay, and right in the center of nearly all those galaxies I've showed you, we think is a very, very, very special object. Okay, now we're zooming in. We're in the bright, dense regions of the galaxy now. So we're in that really bright bit. If you think back to the Milky Way's bright bit in the middle, we're in there. And now what's going to happen soon is we're going to change from a simulation, okay, to a real life video. This is a video of the orbit of the stars right in the center of the Milky Way. And you can see that there's some sort of flashing object, but there's no really massive bright source that these objects are orbiting. Okay, so what you can work out is you can say, well, if all these stars are moving around and orbiting some point in the center of the galaxy, how massive does that object have to be? This is Newtonian physics, and people have done it that are far more intelligent than me, and they calculate that the mass of the object here, which you can just see flash, the mass of this object here is a few million times the mass of the sun, but we can't see it. What could possibly have that mass that we can't really see? The answer: a supermassive black hole. Okay, and this is the key area of my research now. And we need to talk a little bit more about these supermassive black holes, because they're really extravagant objects. Okay, now common perception tells you that you don't escape the gravity of a black hole. Okay, that's true if you get close enough. Okay, but the gravitational field of a black hole, if you think about the gravitational grip of a black hole, extends beyond the event horizon. It's not event horizon or nothing. Event horizon is the point of no more return, but there's still gravitational influence of the black hole beyond that. Now, the real secret about these supermassive black holes, and the thing that makes them really interesting and counterintuitively, is they're incredibly bright if something gets too close to them. So that something is usually gas. So if gas gets too close to these supermassive black holes, what sort of happens is the gas begins to funnel around, okay, well beyond the realms of the event horizon. It funnels round into the gravitational well of the black hole. If that happens, we say that the supermassive black hole is accreting, because that gas is eventually going to fall into the black hole and grow the black hole in mass. Okay, so this is how the black hole grows. It grabs near gas that gets too close. But when I said they're incredibly bright, it's because that gas the gas, as it spirals into the black hole, emits a ton of radiation. And in the most extreme scenarios, when this black hole is having a real buffet, it can outshine entire host galaxies. So what we say that this supermassive black hole is active, it's switched on, because it's got this accretion of gas spiraling into the middle, it's growing. And if you look right in the point source, this is not one of the examples I said where it outshines the whole host galaxy, but if you look right in the center of this galaxy, just above the red point, you'll see a very, very bright white spot. And that is because the supermassive black hole in the center of the galaxy is accreting. And this is where my research kind of comes in now. Okay, so I'm hopefully you're going to be able to keep track with me. I'm going to try and get through this as well as I can. So I said stars form from dense cold gas clouds, right? And I've also just said that gas is required to grow the supermassive black hole in the center of galaxies. Now, the supermassive black hole in the center of the Milky Way is not bright because it's not growing, because there's no gas feeding it. Okay, and in general, we actually only see about 5 to 15% of galaxies have active black holes in the middle. The rest of them are inactive. It's only about 10% of galaxies have black holes, supermassive black holes in the center that are accreting. Sarah Bohr asked, is there a supermassive black hole in the center of every galaxy? Certainly the most massive ones. Certainly the most massive galaxies. It's unknown yet whether those dwarf galaxies that I talked about have a supermassive black hole in their center. And the reason we think... Okay, so I heard somebody there. No. Okay, I'll continue. And the reason we think that the supermassive black hole in the center of every galaxy is because even when the supermassive black hole is not active, which means we can't see light from it, we can detect it by looking at the orbits of stars or gas nearby to the black hole. Okay, now, contrary to popular opinion, and contrary to what I maybe just said, the gravity of the supermassive black hole is nowhere near the size of the galaxy. So if you take the Milky Way's diameter, I said was 100,000 light years, you're lucky if the gravitational influence of the black hole affects the central 1, 2, 3,000 of them. Okay, it's very, very small compared to the size of the galaxy. Okay, thank you, Sarah, for that question.
I got a question from me, if you don't mind.
Okay, yeah,
that is, okay, so how come astronomers come up with such cool names like supermassive black holes that sound like supervillains, and then name telescopes the large telescope, the very large telescope, and the very, very large telescope? Seems like a contradiction.
Yeah, so I actually disagree with the first part of the. I don't think astronomers are very good at naming anything. We call it supermassive because they're not stellar mass and they're not intermediate mass. They're supermassive. And if we ever detected black holes that were generally bigger than supermassive ones, we'd have to call them ultra massive. So this is the pitfall that astronomers fall into. So I assume the second part of your question was in refer to the white paper published the other day about the ultimately large telescope that they're going to build. And this supersedes the very large telescope in Chile and the other one, the 30-meter telescope, the ELT, all these other very extremely large telescope that we call them. I don't know. I'd sooner see telescopes named after, in the same way that Hubble Space Telescope was named after. That's a good name. I think the ultimately large telescope is kind of an ego contest, dare I say. I don't know. I wouldn't have named it ultimately large telescope if it was my idea. But it's a good question. But again, I don't think we name things very, very well. We call this supermassive because it's supermassive. Okay, so yeah, so the final point I wanted to make about these supermassive black holes is that we know it's gas that feeds them, and we know it's gas that drives the growth of stars in the galaxy. So what could that mean? That could mean that if a galaxy had a lot of gas, it could form both stars and fuel its supermassive black hole. If, however, a galaxy didn't have much gas, then maybe it couldn't fuel its supermassive black hole, or maybe it could only fuel it a little bit, and then maybe it couldn't form stars, or maybe it could only form a few stars. So what does that look like in a mathematical picture? Well, that would mean that we'd expect a positive correlation, right, between the black hole growth of galaxies and the star formation. Because if there's lots of gas, then the galaxy probably falls up here. If there's only a middle amount of gas, maybe it falls here. If there's no gas in the galaxy, maybe it's down here. Okay, so this is where we're going to turn statistical now, because we're going to start having a look at some graphs and having a look at some numbers. This is what we actually see, though. So this is a real study from Flora Stanley et al. 2015, and they took, so you get the different, I'll start with the colors. So the colors of these points represent times in the universe. So remember I said there's galaxies that are billions of light years away, the galaxies that are close. Whenever we investigate anything in astronomy, we always have to be careful for the fact the universe have different conditions at different times. So what we do is we split them up into the times of the universe. So 0.2 to 0.5 are the galaxies that are closest to us, and galaxies up here that says 1.5, 2.5, they're galaxies that are really far away. So what you have here is you have the black hole growth on the x-axis, okay, and we have the star formation rate on the y-axis. Now, if you look in the top two redshift group, two time groups, you see that the correlation is actually really flat. Really flat. You've got a very flat correlation in the red, a very flat correlation in the green. There's uncertainty and scattering the points, but there's no systematic correlation. I'd hope you'd agree. Maybe in the pink one there is, maybe, but again, and maybe the blue has a dip and then an increase. We don't know, but there's no systematic positive correlation that I just said we might expect to see. Okay, and Chris mentioned it very briefly in the introduction. How do you? Oh, okay, I've just got a question. Oh, before I go, George and Barbara asked, how do you measure the black hole growth rate? Okay, all we do is dead simple, George and Barbara. All we do is we measure the amount of light from the very, very, very central region. Okay, and what this means, because like I said, when gas is falling in, it's very, very bright. The brighter the central region of the black hole, the brighter the region around the black hole, the more gas that is feeding it. But again, that's tricky. There are a lot of uncertainties on that, as there is in everything in astronomy, but we measure the light. So in particular, we use, the way I use is I use light in the X-ray band, because there isn't much else in the galaxy that's bright at X-ray wavelengths. The light produced from that gas from falling in is bright everywhere, from radio waves right through to X-rays, and the host galaxy is not always as bright at all them wavelengths. So we try and pick and choose the ones that work best. So why are there more measurements for the more distant galaxies and hardly any for the nearer galaxies? Okay, now I think that's right, Sarah, what you said, but I need to just tell you a little bit more about this graph first. These points don't represent individual galaxies. They represent small groups of galaxies. Okay, so it's probably true that there are a lower number of measurements in the more local universe, as in the blue points, and I think, but I'm not entirely sure, I think the telescopes we have, the instruments that we have to measure the so the star formation rate here is measured at far infrared wavelength. So there's the infrared to radio end of the spectrum. And as the further away a source is, the more redshifted the light from that galaxy is. So it's easier to detect infrared from galaxies that are slightly further away. And in particular, I think Herschel's generally better at more distant objects than it is nearer. But it's a good question. I should look into that a bit more. I think it's something to do with the detection rate of the far infrared regime is easier to detect galaxies that are about Z1, Z1.5, Z2.5. It's very difficult to do locally. I know that from my own studies, actually, but I'm not 100% sure why. So a good question. I'll see if I can find out. George and Barbara asked, do black holes only grow from gas, or do they also absorb stars? They do absorb stars, but very, very rarely. So this is something that the group in Sheffield has worked on a little bit. I know a little bit about this. I'll try not to. I'll try and tell you what I know. So when a star gets too close to the supermassive black hole, depending on the mass of the star and the gravity of the black hole, the star can either be stripped, as in like pulled apart slowly, or swallowed entirely. And I think there'd be differences between them, but I think what happens then is you get an incredible increase in the brightness, a very, very sharp increase. And the reason being is because all the fuel from a star would go very quickly. If you've got a large cloud of gas, it might fuel the black hole more slowly for a longer extended period of time. So when it absorbs stars, what you usually see is what we call a tidal disruption event, and it's a flare in the light. It shoots up and then comes down very, very quickly as well, because it's like had one big plate of food, like I say, rather than the buffet analogy I used. Okay, so the interesting thing, and I said, just going back to Sarah's point, I need to talk about this graph a little bit more. These small points, and Chris alluded to it in the introduction when I wrote for the blog on the weekend about averages, for reasons that are complicated, these points are not individual galaxies, they're small samples of galaxies. And then what they do is they take small groups of galaxies that have similar black hole growth properties, and they calculate the average star formation rate. Now that's true, and I said I'll explain it. The reason that happens is because the vast majority of these galaxies do not have a detected threshold of star formation rate. So what you can think is that if we can see a supermassive black hole eating, because that's very, very bright, we know the galaxy is there. But if we don't detect any star formation at our, in this case, infrared wavelengths, that means that the star formation that's happening in that galaxy is below what we could have detected. So what you actually have is you have an upper limit on the star formation, right? Because if it was above that threshold, we would have detected it. And the way you can get around that is a process in astronomy called stacking, where basically you add all your non-detections together. So if you imagine you've got a picture of lots of galaxies that don't have a detected level of star formation, if you add them all together, eventually you end up with one super galaxy, as it were, where the signal to noise in that image is above the detected threshold. But the problem with that is it only gives you a summary average statistic. It's not an average it's not a real true detection. So if you just plotted actual points on this graph, the vast majority of them would be upper limits, which means you couldn't really derive the correlation anyway. So just to go back, just cover that point again in more detail. I really need to hammer this point home. We start with a sample of galaxies similar to the Hubble Ultra Deep Field, and this is the study of Flora Stanley 2015. I've just shown you, and they group them into smaller samples based on their black hole power. So I've only chose 3 here for the example, but there was more in the previous one. So you group, say, black hole growth low, black hole growth, intermediate amount, black hole growth a high amount, and then they look at all the star formation rates in that sample, and they take the average. They look at all the star formation rates in this sample and take the average, and so on. And then the take-home point from the study was that there's no difference between the average values. Now, a passionate topic of mine is that the average value doesn't really tell you everything. And I think people know that. But I think we attribute more weight to averages than I think we should. Okay. So my stats question is, just because the averages are the same, or not different, I should say, does it mean that the star formation rates that produce them average are? It's obviously no, right? So, and here's a toy example. Imagine the star formation rates in the low sample were 1, 1, 10. Well, the average of them is 4. But that's different to the other 2 sample examples here, where star formation rates say 147. I don't know what the units are, but it's just numbers compare. 147. Well, the average is 4 again, but that's not the same star formation rates as the first sample. And in fact, even more scary, if you look at this top example, 1, 1, 10, well, there's 2 values that are 1, so maybe that's the an expected value, a good value of star formation rate for these galaxies. But then 10, that could be an outlier, it could be a typo, I could have accidentally pressed 0. Anything like that. So the final example, even more worrying, is that they're all 4. And obviously the average of them is 4, but you would not be able to see these differences in the true sample, because if you were just looking at the average. In fact, they'd be indistinguishable. You'd think they're the same, and they're not the same. Okay. So okay, so George and Barbara have a question. If the black hole growth rate is based on its brightness, does that mean that you need to be able to observe Cepheid variables in those galaxies? Is that really possible for a galaxy that is at Z2 2.5Z? Okay, good question. There are other ways we can detect. We can calculate different distances to objects. George and Barbara, we don't just need to rely on Cepheid variables. And in fact, nowadays, we don't even need to know the true brightness of sources that are far away. As what happens when light travels through space is that it gets redshifted. And the reason it gets redshifted is because of the expansion of the universe. Now, 100 years ago, the expansion rate of the universe, I don't think was very well known. But now we know the expansion rate of the universe, we can see how redshifted a spectrum is to the some. If you take a spectrum of a galaxy, you know that there are some prominent emission lines that you are going to detect. So that means that the galaxy is going to be bright at very specific wavelengths. Okay, and you can calculate the distance of them. That brightness is from where it should be, and then using the expansion rate of the universe, you can calculate how much the light has been redshifted, which gives you an accurate measure of distance. That's called, now whether you do that using photometry, which is pretty much just like a color telescope, a color camera, or spectroscopy, which is a little bit more detailed, means you can pretty much get quite accurate distances using this new technique of the expansion of the universe. So you don't need to now, I mean, what you've said, George and Barbara, is we calculate distances to more precision when we know some brightness of some objects in that galaxy, but we don't need to know the true brightness of galaxies anymore to calculate the distance, because we know how much the light should be redshifted as a function of distance. But another really good question. So, okay. Where was I? So I said that just because the averages are the same, it does not mean that the star formation rates that produce them are the same. Okay, and that's what I think is key here. So what happens if we look beyond the average? Because the average is only a summary statistic. So how can we just look at, why don't we just look at these samples themselves? Well, don't forget, we've got to still account for upper limits. And the way I do that is by using something called Bayesian statistics, which means that I can calculate those upper limit values slightly differently to the stacking procedure that I told you about that has been used in other studies. So, and the next slide is the final slide of the presentation. So, and then we're full discussion, full steam ahead. Oh no, it's not. I lied. I lied. There's 2 slides left. So what we did in our study is we took a sample of galaxies that I'm going to put in red, which had low supermassive black hole growth. Okay, so supermassive black holes that are not growing, but not growing too fast. And I took a sample of galaxies. Well, we took a sample of galaxies that are in blue, and they're the ones that have got really powerful supermassive black holes. So they're the ones that are eating lots. And then I calculated what we call the full distribution of the star formation rate of the galaxies that they were in. And this is the results from that paper. So in red, as I said, there's the galaxies with less supermassive black hole growth. So here's the star formation rates on the bottom, and I've just got a histogram here using my Bayesian methodology. And I've got the blue galaxies. The galaxies in blue are the ones with the most supermassive black hole growth. And what you can see here is that there are subtle differences in the full sample. Now, the burning question is, well, these 2 distributions don't have the same average. They have more similar averages than meets the eye, because this star formation rate here is in what is a logarithmic scale, which means that if you calculate averages, you're dominated by the larger values that are on the right-hand side, as opposed to the very small values that are on the left-hand side. So what do we see here? Well, let's have a look at these histograms in more detail. You'll see that the galaxies with more supermassive black hole growth has a narrower range of star formation rates. In particular, they don't go down to these low star formation rates down here. that the galaxies with less supermassive black hole growth can. And the other interesting thing is that the distribution looks shifted. It's as if somebody's pushed it over to the right slightly. The peak is at different positions. So it means that, you know, the modal value, not the mean value, the modal value is shifted slightly. So that just can be summed up simply by saying that galaxies with more supermassive black hole growth tend to have more consistent ranges of star formation and very slightly systematically higher. Whereas the galaxies in less supermassive black hole growth tend to have a wider range of star formation. As you see, some of them have the right edge of it. There's very little difference down here. The big difference is on the left, where you see that actually galaxies with less supermassive black hole growth can live in galaxies with much lower amounts of star formation. But that answers that question that I posed right back in the middle of the talk. If gas is fueling both these processes, it's a result like this that you would expect to see, because the galaxies with more supermassive black hole growth don't have the lower levels of star formation that we see in galaxies that have less supermassive black hole growth. And that all supports the idea that they're fueled by the same gas, that they're fueled by gas. So galaxies with lots of gas are likely to fuel the supermassive black hole and provide more consistent levels of star formation. Just thinking back to them little tiny red dots in the Milky Way at the beginning, more consistent star formation. Okay, so hopefully I've given you an example of how just being a bit more careful with our statistics. As I said, I didn't want to talk too much about statistics because I know it can be quite boring, but hopefully I've given you an example there of how being more careful with our statistics, not trusting averages entirely, asking questions about going deeper, have shed light on the supermassive black holes in the center of galaxies and how they grow in relation to the galaxy itself. So I'll just leave you with two final take-home points. The Hubble Ultra Deep Field on the left is one of the most, hopefully I've managed to convince you, if I haven't, I've done a bad job, one of the most interesting images in science. It's a three-dimensional image with 10,000 galaxies, each with 100 billion stars in a fraction of sky, the size of 1/80th of the moon. And just the final point on average is just remember on average that humans have less than 2 legs, just to prove up on averages. So that's everything from me on the talk.
Averages mask a lot of things, don't they?
They do. They can be at best. At best, they are honest but not descriptive, and at worst, they're misleading. So yeah.
Thank you, Liam. That was a really engaging and informative talk, and I loved the way you handled the questions yourself, which is good. It saved me a lot of bother, so I was live tweeting it.
Oh, thank you.
That was very, very fascinating indeed, and we'd like to thank you. For those of you who are here, we have a method of thanking people, and that is you'll find that there's a raise and lower hand button. So if you watch Liam, you'll see the raising and lowering of hands, which is a simulation of applause on there from those who are joining us live.
Thank you.
Thanks to those of you who joined us on the live streaming platforms. I'm going to terminate those in a moment. But those of you who are here on the Zoom, Liam, are you able to stick around for a few minutes?
Of course, I can answer. I'll try and answer questions.
Yeah. Okay. If you would like to join in a sort of informal live chat about Cafe Sci, astronomy, or just talk to Liam, would you please raise your hand and leave it raised, and then I will promote you all, those who want to panelists. And what will happen then, I think, is that the screen will suddenly disappear for you, but it will then come back again. So you'll get a sort of little disjunction in it. So if you raise your hand, then I will promote you to panelists. Anybody else? I'll give you a few minutes to respond to that. You're more than welcome to. You can just monitor the talk if you want to, or you can join in. Okie dokie. That's those of us. All right. I forgot to terminate the live streaming. So goodbye to those of you who are following us on the live streaming platforms. Hope you enjoyed the talk. I think I was a few minutes late on starting the live streaming, but all you will have missed is part of my introduction of Liam, so you should see his entire talk. And if you want to follow Cafe Sci, go to cybercafe.science, which is the website. .science is the domain name for that, and you'll find that you can join in any of these then. Goodbye from me and goodbye from Liam, but hello
Bye.
to those who are joining the panel.